Hello friends, we are discussing chemical kinetics, and in chemical kinetics now derivation of rate constant of nth order reaction with equal initial concentration. We have derived rate constant or specific reaction rate or velocity constant for zero order reaction, for first order reaction, for second order reaction with equal initial concentration, with unequal initial concentration, for third order reaction with equal initial concentration. So now derivation of rate constant of nth order reaction with equal initial concentration. So for that we are following same steps. First we have to consider the general reaction with nth order, then we have to apply the rate law, then we have to apply the definition of rate, and then by equating as per definition as per rate law, derivative term is there, remove the derivative by taking integration, then you are getting rate constant for nth order reactions. So in all derivation similar steps are there, so follow these steps. It is very easy, you can get derivation of any order reaction. So consider a general chemical reaction having order n with equal initial concentration. So consider this reaction. Na gives product. Initially when T is 0, product was 0, let concentration of one reactant is A at time 0. Initial concentration it is. At time t, we are studying reaction till time t, imaginary time t. So let X be the concentration of product. X product is formed. So at that time, concentration of one molecule of reactant is A minus X. So A minus X is the concentration of reactant at time t, and then apply rate law. So by rate law, rate of reaction is directly proportional to concentration of A minus X. It is nth order, experimentally determined term n. So therefore raised to n. And therefore rate is equal to Kn. Kn is a rate constant or velocity constant or specific reaction rate of nth order. So this is your equation number 1. Now by definition of rate, rate is equal to dx by dt. This is your equation number 2. Now from equation 1 and 2, that you can write from equation 1 and equation 2, this Kn A minus X raised to n is equal to dx by dt. We have to write the derivation of this Kn. We have to find the equation of Kn, but in this equation there is derivative term. So as usual, to remove derivative we have to take integration, but before taking integration, similar variable, x variable should be x side and other should be other side. So that way we can rearrange this equation. So this equation we can write another way. So therefore Kn, take dt this side, change party, change sign, Kn dt is equal to dx upon, take A minus X that side. So A minus X will be divided here, raised to n, and this is your equation number 3. So now take the integration of equation 3. take integration of equation 3. Integration of kn dt 0 to t, limit will be 0 to t for time, is equal to integration of, we can write this way, 1 upon a minus x raised to n into dx. Instead of writing dx here, I am writing here. And for x is concentration of product. When time was 0, product was 0. At time t, product was x. So 0 to x. Therefore, here kn is constant. Take constant outside the integration. So constant kn 0 to 2t into integration of dt is equal to, now we have formula x raised to n, integration of x raised to n dx is x raised to n plus 1 upon n plus 1. So take this one denominator at numerator. If we are writing this way, a minus x, then it will be minus n into dx, limit 0 to x. So what we have done, a minus x, there was plus n, we have taken it at numerator, change the numerator to denominator, sign will be changed. Here denominator we are taking to numerator, then power sign will be changed. So here plus n, here minus n. So both are same only. Now we are applying integration formula. Therefore kn 0 to t dt is equal to, apply integration formula. That formula, a minus x raised to minus n plus 1 upon minus n plus 1 into dy dx of, don't forget to take the derivative of a minus x 0 to x. What we have done here, so note down, this is equation number 4. We will solve this one. But what we have done, we have applied this formula, x raised to n dx is equal to x raised to n plus 1 upon n plus 1, this one. And if such function is there, we have to take derivative of that function also. Only x, no problem, because derivative is of x is 1. So this is we have applied, this is the formula. So solve equation 4 properly. So we'll solve equation 4. By solving equation 4, see, by solving equation 4, here integration of dt is t, lower limit 0, upper limit t. Kn is outside this. Kn keep as it is. Take the integration of dt. Integration of dt is t, only t. So written here t is equal to. Simplify this one. This is what? A minus x raised to minus n plus 1 upon, this is minus n plus 1 into derivative of a. Derivative of a is 0 and derivative of minus x is minus 1. Lower limit 0, upper limit x. Again solve this one, simplify this one. So after simplifying, we are getting therefore kn, upper limit here, upper limit minus lower limit, t minus 0, lower limit is 0, is equal to integration of a minus x minus n plus 1 upon minus n plus 1 into minus 1, by multiplying this minus 1 inside this bracket. So minus 1 into minus n become plus n, and minus 1 into 1 minus 1. So this one we can simplify here. So therefore kn t is equal to a minus x raised to minus n plus 1 upon, at denominator you are getting n minus 1. So this is limit 0, lower limit, upper limit x, 0 x. Therefore, K and T is equal to, take this numerator at denominator and take this n minus 1 is constant, so you can take it common outside the bracket. So 1 upon n minus 1, and this one we are taking at denominator, so we are getting a minus x raised to. Now numerator I am taking to denominator, so minus n become plus n and plus 1 become minus 1. So this way power sign will be changed, so 0 to x. Now we will solve this one by applying upper limit minus lower limit. I am writing here only K and T is equal to 1 upon n minus 1 into, now apply upper limit, upper is x, instead of x put x, so already it is there, a minus x raised to n minus 1, so there is no problem. Now minus lower limit, instead of x we have to put 0, so 1 upon minus 1 upon a minus 0 raised to n minus 1. This one we will simplify up to here step by step. See the equation how we have written all the equations. Now go ahead, and after simplifying that equation we are getting K and T is equal to 1 upon n minus 1 into 1 upon a minus x bracket raised to n minus 1 minus 1 upon a raised to, a minus 0 was a, so a raised to n minus 1. So therefore Kn is equal to 1 upon, take t this side, so n minus 1 into t, so this one 1 upon a minus x bracket raised to n minus 1 minus 1 upon a raised to n minus 1. So this is your equation number 4. Kn is equal to this one, and this is the rate constant of nth order reaction. But in this case n is not equal to 1. If you are putting n is equal to 1, fair, note down, n is not equal to 1. Why not equal to 1? Because if you are putting n is equal to 1, 1 minus 1 will be 0, and 1 upon 0 is infinity. No one discovered that is how much, so we don't know that value. Therefore it is not applicable for first order reaction, and we know that for first order reaction rate constant is in terms of logarithm. So this equation is applicable for 0 order, second order, third order, fourth order, fifth order, sixth order with equal initial concentration. So necessary condition is what? Equal initial concentration, and order should not be 1. So for that it is applicable. In this equation if you are putting n is equal to 2, second order, so you are getting K2 is equal to 2 minus 1 is 1. So 1 upon t into 1 upon a minus x, 2 minus 1 is 1, minus 1 upon a. So this is the rate constant of second order reaction. We have derived this equation with equal initial concentration. Then if you want to remember third order reaction, so just put here 3. So 3 minus 1 will be 2. So that means instead of n minus 1, you have to put here 2, here 2, here 2. Then that will be third order reaction. K3 is equal to 1 upon t, 1 upon a minus x. Here 3 minus 1 is 2t. Here 2 minus 1 upon a square. Means what? If here 3, then here 2, here 2, here 2. If here 2, then here 1. A power is 1 here, bracket raised to 1 and a raised to 1. So this way. So this is for rate constant of second order, this is rate constant of third order. Similarly for fourth order, what will be there? K4 is equal to 1 upon 3t into bracket 1 upon a minus x raised to 3 minus 1 upon a raised to 3. This is for fourth order. So this way, by using this nth order equation, we can calculate, we can derive rate constant of any other order. But necessary condition, equal initial concentration, and n should not equal to 1. So first order, for first order it is not applicable. For 0 order it is applicable. You can check it. So for 0 order, k0 is equal to x upon t, you will get that value only. K0 is equal to x upon t. So it is applicable. So this way you can find rate constant of any order by using nth order. So nth order is important. So remember the steps. First, what? In all order, when we have derived, first we have considered the general reaction, then applied rate law, then by definition of rate, then both the equation by rate and by rate law we have equated. In a derivative term is there. To remove the derivative, we have taken integration. By applying the integration formula, we are getting the equation in terms of k, that is rate constant, and as per order we are writing k0, k1, k2, k3 dash 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 kn. So this way you can derive the rate constant or specific reaction rate or velocity constant of any order. Remember all those steps, remember the equations. So these are important. This equation especially is important to solve the problems in JAM exam. So remember this equation from nth order you can find for any order. So thanks to all of you and have a nice day.